Everything that tangibly exists in this universe is known as matter. Yeah, but what, I mean, what does that mean? Can I hold it in my hand? Can I breathe it in? Matter has mass. That's what it means. So it takes up space. And it also has a state of charge. And I'm sure that you're thinking, oh, positive and negative charge. Yeah, but there's also the state of having no charge. Elements are identities of matter. So there are things made up of oxygen, carbon, nitrogen, and all of the other elemental identities that are listed here in the periodic table. Usually, this is the point where some student will ask, where do atoms and molecules come into play? Soon. Next slide. No. In this class, we're going to come to understand the abbreviations for many of these elements. You don't have to memorize them in this class. We'll become familiar. Some are intuitive, such as O for oxygen, H for hydrogen, and so on. But some of these abbreviations refer to the Latin root word. The prefix nature stands for sodium and making its abbreviation Na. The prefix cal stands for potassium, giving it the K abbreviation, which is often confused for calci, which is the prefix for calcium, which is Ca. So notice how the second letter of the abbreviation is always in lowercase. And the numbers you see here, these are called the atomic numbers. And they are not just let's line these up and number them. These atomic numbers all indicate something very specific about um, these about an atom or about matter that's made up of these things. Yeah, let's just leave it at that for now. Solid water, known as ice, is less dense than liquid water. In other words, ice floats. Do you realize how unique this is? Like for almost all known substances, the solid form is denser than the liquid form. If you were to make frozen gasoline cubes, for example, the solid gasoline would sink to the bottom of a glass of gasoline. I mean, I don't know why you'd want to do that, but that's what would happen. The key to understanding water's different states of matter, solid, liquid, and gas, is in the orientation of its hydrogen bonds. Solid water or ice has a really precise arrangement to take advantage of the maximum possible space. And this just means that the hydrogen bonds are fixed, like in a crystalline lattice. Liquid water has hydrogen bonds that are constantly breaking and reforming, which might help you understand why water can take the shape of its container. And water vapor, or water in its gaseous state, it has no hydrogen bonds. It's like little disarticulated Mickey Mouse heads like floating everywhere, which is possibly a nightmare for some people. Probably the first chemical formula you learned was water, which is H2O. H2O, water, it's actually a molecule, which is a collection of atoms with different identities. Humans are always limited by their current technology. And today, atoms, they seem to be the smallest packet of matter that we can possibly investigate. However, we know that atoms are made of things called subatomic particles, right? Subatomic because they're smaller than an atom. Subatomic particles are protons that we can note as P with a plus superscript, electrons, that's E with a minus superscript, or neutrons, which is an N with a zero for no superscript. Protons and neutrons, they reside in the juicy filled nucleus of an atom, which is the center here. Both of these areas here are the juicy filled nuclei. So if your protons and neutrons are not in your nuclei, you should probably seek medical attention from a doctor. No, actually, from a physicist, I guess. Anyway, electrons are flying about the nucleus. They contain energy because they're in motion. And electrons are not flying about randomly, even though it seems like that. They are not. But they're organized into these things called shells. Shells are not orbits. Like the orbits that the planets use to circle the sun, that's not what a shell is, right? Because that's just one pathway. But like the shell on a malted milk ball, like Whoppers or any chocolate coated candy, that's what the shells of atoms are arranged like. Not orbits, but shells. The first shell closest to the nucleus can only hold 2 electrons. And we can see that in both of the atoms that I have pictured here. They are both holding 2 electrons in their first shell. So now, if the first shell closest to the nucleus becomes full and the atom has more than 2, then electrons are going to overflow into the second shell, which can hold 8 electrons. And as you can see with both of these molecules that I have here, neither of them have filled that second shell. If the second shell does become full, electrons will overflow into a third shell that also holds 8. We might once use that. No, twice in this class. For this class, we can limit it at these 3 shells, but shells don't have to hold their maximum number, right? It's the maximum number that they can hold, but we're going to see how it's determined what number of electrons they do hold. There are some things that you have to know about shells and electrons. These are like 2 rules. Shells like to have their shells full. They like to be full. They don't like it when they're not full. So these 2 atoms that I'm showing you here, they don't like that. They don't like to be not full. Also, electrons like to be in pairs. They do. They don't like to travel without a partner. The number of protons an atom has depends on which element it is. The atomic number of each element that we can get from the periodic table, that tells you how many protons an atom of that element will have. For example, here, hydrogen, its number on the atomic table, on the periodic table is 1, and therefore hydrogen has 1 proton. I can do another example over here, is that carbon's number is 6. And therefore we know that carbon has 6 protons. Great. Since we're talking about atoms on this slide, it's also appropriate for us to understand that an atom, by definition, has no charge. So if an atom has no charge, this means that the number of protons should be equal to the number of electrons, I can't erase, for the number of electrons. And that's also true for carbon over here. If carbon has 6 protons, it means that carbon has 6 electrons. Sodium has 11 protons. Sodium has 11 electrons. Do you want me to keep going on, or are you picking up what I'm laying down? You're picking it up. Okay, so the atomic number gives me the number of protons in the nucleus, and then I can figure out the number of electrons that will be flying around the nucleus in shells. But what about the neutrons? I still have one subatomic particle that I need to know. The atomic mass can help me with that. The atomic mass is the sum of all protons and neutrons. So let's say that again. The atomic mass is the sum of all of the protons plus the neutrons. And therefore, we could also say that the atomic mass is the weight of the nucleus. Either way you want to say it, we can easily calculate the number of neutrons left, right? So if this is true, that our atomic mass equals the number of protons plus the number of neutrons, I can get the atomic mass from a table, and I know we have 1 proton, so what is the number of neutrons in a hydrogen atom? It's 0. And as you can see from my picture here, I have also not pictured any neutrons. It would be good for me to tell you that the atomic mass of carbon is about 12, and therefore we could also calculate this, that 12 equals our 6 protons plus some number of neutrons. And then we can do a little cross math to figure out that there are 6 neutrons in calcium. Oh, geez, 6 neutrons in carbon. Okay, all right, so this periodic table here is not so much of a conundrum anymore. The periodic table of elements, it organizes things by number, but it also organizes things by all known chemical elements based on their properties, right? So it organizes them based on their subatomic particles. And this helps us understand how elements relate to each other and how it predicts their behavior in chemical reactions. This group over here, group number 1, is the alkali metals group. These are highly reactive with metals like lithium, sodium, potassium in there. This over here, this is the noble gases group. These things don't react with anything. Things like helium and neon are very stable atoms and they're unreactive. Their electron shells are full. They don't care to trade or gain from anybody else. So the periodic table, it allows chemists, well, it allows you to predict how elements are going to behave in reactions. For example, elements in the same group tend to have the same chemical behaviors. So it helps scientists understand how different elements are related to each other based on their electron configurations, their atomic structure, and their physical properties.